Hi, everyone. So last week we took our time to discuss some very general things, very basic fundamental things. And what I would like to do now is I would like to go back to solving concrete problems. And then in the remaining time, for the last several days, we'll do a little bit of three-dimensional quantum mechanics. So as far as solving concrete problems in the trenches, we spent some time discussing bound states. So let's very briefly review the setup. Let's very briefly review what we mean by that. So problems in quantum mechanics are defined by the potential energy of interaction of a particle with something else, with the rest of the world. Right? You specify potential energy, you specify the physical situation. Just like in classical physics, if you specify the force, you specify the physical situation. So we discussed potential energies. We discussed potential energies, U as a function of position. We're doing everything in one dimension for now. And a potential energy might be something like this. Remember, you can always shift potential energy. You can always add any number to potential energy as long as you do the same thing to a total energy. It's completely okay. An actual value of potential energy is completely irrelevant. What matters is it changes in potential energy. But if you do add some number, you have to do the same thing to the total energy. And typically, potential energies go to some constant at infinity. It's more common to shift the value of potential energy so that that constant becomes zero. Then we have a situation like this. Let's review what happens classically for various values of energy. So if your energy is below the potential energy at infinity, so then you would have bound motion classically. Or a wave function that corresponds to a bound state quantum mechanically. So in classical physics, we would call it bound motion. For example, this would be some kind of a particle oscillating back and forth, or this is called the bound state in quantum mechanics. And various types of bound states can exist. So for example, you can have something that I just drew, or you can have a harmonic oscillator, for example, or you can have electron interacting with a proton, right? So this is like a basic, like a hydrogen atom. Or this could be an electron in an ion, right? So the plus doesn't have to be literally a proton. It could be just an ionized core of an atom. And depending on the potential energy, you have a different ladder of states with different energies, with different values of quantized energies and different wave functions. I'm noticing that some students still confuse wave functions with energies. Okay, you have in quantum mechanics, you have a ladder of wave functions, and each wave function has its own energy. Okay, so in the first case, you have different states of the harmonic oscillator. In second states, you would have different states of an atom. We didn't discuss atoms yet, but I emphasized this qualitative similarity between different bound states. When we're doing this in one dimension, the motion of a negative charge, the bound motion, when we do this in one-dimensional classical physics, the bound motion of a negative charge with a positive charge in one dimension is a pathological problem because it requires the negative charge to go through the positive charge. That solution exists, but it's not commonly talked about. But in 3D, the picture on the right corresponds to a genuine atom. So classically, so this is classically, so this is, let me separate this. Bound motion in 3D, or let's say in 2D, is like this. So you have a negative charge orbiting a positive charge, which is exactly the same physics as Earth orbiting a sun or moon orbiting the Earth. And bound motion would be elliptical motion or circular motion. There is a one-dimensional solution where the negative charge shuttles back and forth, but it would pass through the positive charge with infinite speed. That solution exists. It's not very physical, right? It doesn't happen. This is more relevant to 2D. For harmonic oscillator, 1D is a 1D, classical harmonic oscillator in 1D is a meaningful situation. So this, for example, you could have something like this, that this shuttles between the turning points, or I told you that it's basically equivalent to this, particle. So you can have this kind of situation, a diatomic molecule or some kind of a dumbbell that's oscillating back and forth, or I told you that it's equivalent, it's basically equivalent to effectively a single particle oscillating around the equilibrium point. So these are just two examples, two relevant examples. Lots of things behave as harmonic oscillators, and of course atoms are relevant. So these are classical examples, and quantum mechanically we get quantization. So that's bound states in classical physics. I'm sorry, bound motion in classical physics, bound state in quantum physics. What happened, and then of course, we did talk about harmonic oscillator. I gave you the solution. We did not yet talk about atoms, but we did talk about models. I'm hoping that one thing you can get out of this class is the appreciation for the importance of models. It's not specifically a quantum mechanics idea, but models are extremely useful. Physics is the art of squinting the eye at the universe and making it comprehensible, right? So Einstein said that the most incomprehensible thing about the universe is that it's comprehensible. Why is it comprehensible? That's an interesting question. And we used finite well or even infinite well to model both of these situations. Of course, the results will differ in detail. They will be quantitatively different, but qualitatively they share similar features. Why do we do this? Because qualitatively, the result will share similar features with more realistic situations, and also because this is a workhorse. This is our work horse. Of course, if it did not share qualitative features, then we probably would not be using this workhorse. So again, we get a set of levels, we get a set of wave functions, and you get bound states when energies are lower than the top of the potential energy. So this is, we had a setup that looks like this, right? So this was 0, this was L, this was U naught, right? And I even mentioned that, well, it's a model, but you can actually construct a physical system like that in the lab by having two capacitors that prevent a charge from escaping, right? So you apply a delta V here, you apply a delta V here, and let's say if it's a positive charge, there's a strong electric field that prevents that positive charge from escaping, and it will just ping back and forth between the two capacitors, right? So you actually can construct this. Okay, so that's the review. I can go back to this generic potential energy, and I can ask, what if the potential energy, well, I'm sorry, what if the energy is larger than potential energy at infinity? So what if you have something like this? Okay, let's discuss classical situation. Well, what does this describe? This describes a particle that has some kinetic energy, and when it passes in the vicinity of this thing, whatever it is, it could be some smooth charge distribution, like a solid, a charged solid, it gets kinetic energy boost at the expense of losing potential energy, and then the kinetic energy is lost again. So it's a particle that speeds up and slows down, and it moves off. So it moves in from minus infinity and moves off to positive infinity. Speaking of atoms, so here's a interatomic potential energy. So I'm going to place the atom at x other than 0. You can do this in 1D, where the negative charge passes through the positive charge, but the 1D situation is pathological. So 2D on bound motion of electron moving past a positive charge, or moving past an ion. So what would that be? Well, so here's a positive charge, and commonly it's drawn like this. So you have a negative charge moving in from minus infinity. Far away, it doesn't feel the positive charge. But when it passes the vicinity of the positive charge, it gets attracted, it gets deflected, but its kinetic energy is so large that will not be captured by the positive charge. So it would follow a hyperbolic trajectory. And this is a very typical scattering situation. This is scattering. Okay. So if the energy of electron is too great, if it has enough kinetic energy, it will be deflected by the positive charge, but will not be captured by it. So that's the scattering. So this corresponds to this. So this is energy. By the way, the red are energies, right? So these are all E1, E2, E3. I'm so used to using red for energies that I didn't label it. Right? So this is, if you have a potential energy like this, if you have a negative charge in the vicinity, moving past the positive charge, in 2D it would look like this. In 1D, there is a solution. It's a very pathological solution. No one ever talks about it, but it does. In 1D, this really would correspond to an electron speeding up, acquiring infinite kinetic energy, moving through the positive charge, and then losing energy, and then having some residual energy. That solution does exist. It's not, we rarely talk about, but in 2D, it's more relevant. This is scattering. Or you can have exactly the same thing for gravity. You know, electrostatics and electricity or electric behavior and gravity, they're similar. So you could have the sun, and you can have some kind of a comet, right? So comet. This is a stray comet. A comet that orbits the sun actually follows an elliptical trajectory, then it's bound. So this is just to be clear. So this is classical unbound motion. And what I'm trying to emphasize is that this unbound motion is a scattering motion. So this is why when we go back to quantum mechanics, when we quantize this situation, when we ask ourselves, what is a quantum solution for the case when the energy is greater than potential energy, we will call it a scattering state. Okay. So again, I'm contrasting classical and quantum, right? I talk about classical bound, then quantum bound, classical scattering, and now we will talk about quantum scattering. And to do that, we will again use our workhorse. Okay. You can actually build it in the lab. So what would correspond again? But before we do this, quantumly, let's do this classically again. So this corresponds to a particle moving without any force, derivative potential energy is 0. Then it gets a force kick and it accelerates. It moves faster within the well, and it gets a force kick in the other direction and it slows down and then it moves slower. So an example of that is a charged particle. Let me drill a hole here to allow the particle to pass. You can have a positive charge getting a boost of kinetic energy as it passes through the capacitors. It really should be a straight line, right? So this is positive charge, gets a kick, it accelerates, and then it gets a kick in the other direction that it decelerates, right? So it has some kinetic energy. So it has kinetic energy 1. Then here it has kinetic energy 2, bigger than kinetic energy 1. And then it gets back kinetic energy 1. So that's what this corresponds to. And now we're going to use the workhorse to solve the quantum mechanics problem that is called the scattering state. So that's the setup. I really wanted to kind of give you the big picture review, explain why we're doing this. And now let's roll up the sleeves and actually do that. I will set up the math. I will skip some details of the math because you already get the picture how this works. And this is also discussed in your textbook. But first, let me set it up carefully, right? So, okay, so setup. Again, so I have a potential energy. I'm gonna use the same setup. Let's see, maybe I didn't draw this right. Yeah, no, I did this right. So this is called U naught, and this is X. Some books set it up differently. They set up potential energy at infinity to be 0, and then potential energy within the well to be minus U naught. Some set it from minus L/2 to plus L/2. So it depends. I'm going to stick to this way of setting it up, right? And so, and now we're interested in a situation where energy is bigger than potential energy, like that. Again, you have 3 regions, right? 3 regions. This is region 1, this is region 2, this is region 3. In region 1, the time-independent Schrödinger's equation, again, remember, we use separation of variables. The temporal component to the Schrödinger's equation is just a complex oscillation e to the minus I e over h bar times t. And then all the details of the potential energy enter the time independent Schrodinger's equation. So here, time independent Schrodinger's equation reads the following. Psi double prime equals E minus U naught times psi. Here, it's simpler. And here, it's again the same as in region 1. Okay? What do? We write down the equation. Step 2 is to write down the general solution. Step 3 is to apply boundary conditions. Right? So let's see. So solution in region 1. So I guess I should say general solution. In region 1, it would be, let me call it like this. It would be, so you see this is a constant. Actually, before I write down the general solution, let me rewrite the Schrodinger's equation. Don't worry, I will skip some math. I just want to set it up properly. So what I have is I have, so let me do this. The second derivative equals minus 2m for h bar squared times E minus U naught. This is all a constant times psi. And I'm going to call this k squared because it's a positive constant. E is bigger than U naught. You see, E is bigger than U naught, so it's a positive constant. So it looks, when we clean it up, it looks like this. And then the general solution, we discussed differential equations. The general solution in region 1 will be a combination of this and this. Now, remember this is psi of x. So the big psi is then e to the I k1 x minus omega t plus b e to the minus I k1 x plus omega t. This is a right moving wave. This is a left moving, I should say plane wave. Oh, no, please don't do that. Please don't do that. Just a second, folks. Very delicate. Right moving plane wave. So general solution, including the temporal factors and everything, in region 1, the general solution in region 1 corresponds to the right moving plane wave and the left moving plane wave. Plane wave can be superposed. You might argue that this general solution is not a very good one, not a very kosher one, because it's not normalizable, so we have to build wave packets. True. Okay, we will not discuss scattering of wave packets, it's too complicated. We will discuss scattering of plane waves, just to get the general idea. And then if you want, you can learn about scattering of wave packets at some point in the future. So this is right moving wave and the left moving wave. Mathematically, they're described like this. Okay, so in region 2, region 2 is simpler. you have psi double prime equals minus 2me over h bar squared psi. Let's see, so this is, I'm gonna call this K1, right? So this is called K1. Wave number in region 1. In region 2, wave number is larger because you're not subtracting U naught. I'm gonna call this K wave number in region 2. And so the general solution, again, I'm just going to the time and just the spatial part, is going to be C e to the ik in region 2 times x plus d e to the minus I k in region 2 times x. And in region 3, the same as in region 1, but I should use different names for coefficients. So, because in general, they will be different. A, B, C, D, E, F. So let me sketch what we have. So we have, again, we have region 1. So I have incoming and outgoing wave. So this has coefficient A, this has coefficient B. In region 2, the wave number is larger, so it will be a wave with a smaller wavelength, right? So it will be something like this with coefficient C and something like this with coefficient D. And in region 3, again, it's a B, C, D, E, and this is F. Okay, so this is again right, and this is left. This is, so sorry, this is supposed to be psi 2. This is right moving wave, and this is a left moving wave. So contrast that to a bound state. For the bound state, we had a growing and decaying exponential in region 1 and region 3. And we had to throw out the decaying exponential in region 1 and growing exponential in region 3. And only in region 2 was it a sum of left and right moving wave. Now we're dealing with left and right moving waves in all 3 regions. Okay, so that's the setup. What's the next step that we do? The next step is apply continuity plus smoothness boundary conditions at x equals 0 and x equals L. We also have a normalization condition at x equals minus, so that imposes some kind of condition at x equals minus infinity and plus infinity. The wave we're dealing with here is not normalizable. Again, you have to build a wave packet. We're not going to discuss wave packets, so we will not worry about the fact that it's a not normalizable wave, because this will get across the essence of the idea. In real world, we have to study not scattering of waves, but scattering of wave packets. Physically, what do we expect? Okay, so we're dealing with waves. So before continuing with math, let me guide our thinking. We are dealing with scattering of waves, right? You see scattering of waves. Where else do you deal with scattering of waves? In many things. Here's a prototypical example. Okay, so classical example. You have a rope, and then you tie a knot and a rope. So this is a rope, this is a knot, and this is a rope. I send a wave down the rope. So I can send a wave train, for example, or I can even send a continuous wave. What happens when it gets to the knot? It will be, part of the energy gets reflected, and part of the energy gets transmitted. So this is a right here. Let me use a pencil right here. So this is an incident wave. This right here is a reflected wave. And this is a transmitted wave. It's meaningful to talk about, well, what fraction of the energy is transmitted, what fraction of the energy is reflected. So the amplitude of these waves is related to the energy. Energy is like the square of the amplitude. So the fact that we're dealing with left moving waves, right moving waves, it means that we're dealing with scattering of waves. And what is it scattering off of? Well, it's scattering off of this well. So in quantum mechanics, let's go back to some general situation. This is some kind of a scatterer. I want to go back to the big picture. Let's say you're sending in incoming wave. You're sending in the incoming wave. We're dealing with waves. Waves scatter from any kind of irregularities. In this case, it's off of a knot. This is an irregularity, right? It's not, so here a potential energy is constant, here it's constant, but here there's something going on. It's some kind of a physical scatterer. So there will be a reflected wave. So this is incident wave, and there will be a transmitted wave. Just by virtue of the fact that we're dealing with waves scattering off of irregularities, you will expect a reflected wave and a transmitted wave. But what's waving? What is the wave? It's the wave function, right? In quantum mechanics, the wave is the wave function. So if you have an incident wave function, it's incident on some kind of a scatter. It could be an atom. It could be something else. We're using model as a finite well. It's just a model, but you have a wave function. That wave function will be scattered by whatever this model represents. Part of the wave function will be reflected. Part of the wave function will be transmitted. What that means is that there's a probability to observe the particle being reflected and a probability to observe the particle being transmitted. Contrast that with a classical situation. Remember what I said here. Classically, this just corresponds to a particle speeding up and then slowing down, but it will not be reflected. So classically, you don't expect any reflection. You expect particle moving slow, fast, and then slow, right? So here, positive charge gets sped up by the left capacitor, and then it gets slowed down by the right capacitor. It will always transmit as long as its energy is bigger than potential energy. The top of potential energy, it will be transmitted. In quantum mechanics, without even doing any math, it can get quite technical. Let's step back and see, what is it we're doing? We're doing scattering of waves. You can see that these are waves. Waves scatter. Part of the wave gets reflected, part of the wave gets transmitted. What it means is that there's a probability for the particle to scatter back and the probability to get transmitted. Admittedly, we probably expect transmission probability to be close to 1, but there will be a non-zero reflection probability. That's the interesting part. So going back to the drawing board, what we have to do is we have to apply the smoothness and continuity boundary conditions. So there will be four equations, right? So 4 equations in total. Smoothness on the left, continuity on the left, smoothness on the right, continuity on the right. I'm going to skip some math right now. I'm just going to state a partial process of applying those boundary conditions. When I apply the two boundary conditions at x equals 0, I will relate the coefficients a and b to c and d. That relationship is a pair of equations, but it's more compact to write it in a matrix form. Don't be scared of that. Don't worry if you don't understand it. It's just a compact way to relate the to express the two equations. And that will read like this: 1, 1, k1 over k2 minus k1 over k2 a b equals another matrix 1, 1, 1 minus 1, and this is going to be c and d. So this relates the coefficients c and d to the incoming coefficients a and b. Okay, and you can guess that when I apply the smoothness and continuity conditions at x equals L, I will relate coefficients A, B, C, D, E, F, E, and F to C and D. For completeness, let me just state these equations, just for honesty. Perhaps your textbook does something else. I'm currently traveling. I'm recording this from a hotel room. I prepared this lecture on the plane, so I don't know what your textbook does. The results, of course, will agree. We might have slightly different algebraic forms, but the results will agree, and you're welcome to use whatever you feel comfortable with. So anyway, so it reads like this: e to the I k2l. So it's a matrix, 4 by 4 matrix. E to the minus I k2l, e to the I k2l minus e to the minus I k2l. Matrix acting on C and D equals another matrix, e to the I k1l, the minus I k1l, k1 over k2. So yes, I know, right? It gets quite technical. Imagine working on this on the plane with a N95 mask on, and then you get the full the full pleasure of the experience. Okay, so it's like this. So what I'm going to do is I'm going to combine these two equations to eliminate C and D. And again, physically it means this. So you have an incoming wave and you have an outgoing wave. It scatters from whatever crap it's scattering from. This is a scatter. And then you get a pair of results here. So A, B, C, D, and E, F. So eliminate C and D by combining these equations. Matrix is just a compact form of writing down two equations, right? So I have two equations here, two equations here. I'm going to eliminate two of them to end up with two final equations that relate E to A and B and F to A and B, or vice versa, A to E and F and B to E and F. So this gives me E as a function of A and B and F as a function of A and B. That's what I'm trying to do. And physically, I'm motivated by this idea that you have some kind of a stuff here, then scattering and stuff here. And I want to relate stuff here to stuff here. And I'm not interested in coefficients C and D so much. So that's the story. When I go ahead and do this, I get some kind of results. Okay. But I'm interested in a situation where you have a wave arriving from the left, part will be reflected, part will be transmitted. Nothing will be arriving from the right. Yes, I can look at situations where you have two waves arriving from the left and from the right, but I'm driven by a physical situation where a wave arrives from the left. I allow the possibility that some will be reflected and some will be transmitted. So interested in scattering of the wave. So this is the scattering. And so the result, so this is A, quote, a wave with magnitude A. The result is a wave with magnitude B, and this is a reflected, and this is a transmitted with magnitude E. Okay, so that's the situation. So I have a wave. So this is A e to the I k1x. Some is reflected, B e to the minus I k1x. And this is E to the I k1x. They both have k1 because the difference between the energy and the potential energy is the same. And so I can relate. So I can find the dependence of B on A and dependence of E on A. Right, so when I massage these two equations, what I'm trying to relate here is I'm trying to relate this to this and this to this. Well, okay, so I find those I find those coefficients. So now, what about it? Pause for a second. So remember, what waves are we dealing with? These are wave functions, right? So these are wave functions. Probabilities are related to the amplitudes in front of the wave functions. Sorry, square of the amplitude in front of the wave function. So reflection coefficient of R is defined as the square of the amplitude of B divided by the square of the amplitude of A. And this is a probability of reflection. Since I can relate B to A, I can calculate this quantity as well. And a transmission coefficient called T is the magnitude of the outgoing wave E divided by A. Okay? And this is probability of transmission. I will now state the result for transmission coefficient as a function of energy, right? So remember, the setup is like this. So what I can control is I can control the energy of the incoming particle. This energy or this energy or this energy. And depending on its energy, the probability of transmission will be different. not terribly complicated, but like, what about it? So what I'm going to do is I'm going to plot the transmission coefficient as a function of energy of the, as a function of E, but it's the E of the incoming particle, right? The total energy of the incoming particle. We only are interested in scattering states. We already discussed bound states. So it starts at U naught equals, it starts at E equals U naught. And it will have this kind of a shape. Let me see if you can see this. So this is 1. Transmission coefficient cannot be bigger than 1. So this is the asymptote. Now the amazing thing is it will have oscillations here. And then eventually the oscillations die down. So it looks something like this. Turns out that the reflection coefficient is 1 minus transmission coefficient, which just means that whatever is not transmitted is scattered back. Nothing is stuck inside the well. So we don't really need to talk about reflection coefficient separately. But you see at these spots right here, you have a perfect transmission. You get a perfect transmission, in other words, t equals 1, when the sign is 0. And the sign is 0, right? So when the sign is 0, when the stuff inside the sign equals n pi. So actually, let me summarize what these findings say. Summary of results. First, it's possible to have some reflection. R is not equal to 0. There is a small probability of reflection. Small in comparison to 1. The transmission coefficient is not strictly 1. In particular, well, I should put small in parentheses because it's not small here, right? So if energy is slightly above, actually, let me remove the word small, because there is a probability of reflection if energy is slightly above U naught. How slightly? Well, what sets the energy scale? You have the energy scale U naught. So if the difference between E and U naught is much less than U naught, that's considered slightly above U naught, right? So when this energy distance is much less than U naught itself, that means that the energy is slightly above U naught, right? So slightly above U naught. T is small, probability of transmission is small, and R is close to 1. Okay? So this is very non-classical. Classically, it means that particle is barely moving, then it moves fast, and then it's barely moving again. But quantum mechanically, it says that when energy is slightly above the well, most of the particles, if you repeat this experiment, they will be reflected. They will not be transmitted. Point 2 is, well, okay, so as E grows, reflection decreases, probability of reflection decreases, and T increases. But R, reflection probability, is generally never 0, except, this is point 2, there are special energies when reflection is 0 and transmission is 1. So at those special energies, the well is completely transparent. So this happens when L times 2m over h bar squared times E equals n pi. Right? You see, you go back to this formula. Whenever this stuff right here equals to n pi, the sign is 0 and t becomes 1. In other words, this happens at energies equals to n squared pi squared h bar squared times 2ml squared, which are exactly the same energies as the energy of the infinite well. Okay, so you have a probability of transmission and reflection. If energy is slightly above U0, reflection coefficient is close to 1. Probability of reflection is quite large. As E increases, the probability of reflection decreases, but generally it's still non-zero, except at this very special points when the probability of transmission is 1. Transmission coefficient is 1. And that's basically what I wanted to say for today. Just one second. That is quantum scattering. This is very, very basic quantum scattering in one dimension. Next, what I would like to look at is I would like to look at this situation. Now, you can look at a variation of what we did today like this. So classically, this means particle moves fast, then slow, then fast. But we will look especially at this situation where classically the particle comes and reflects. It will not be transmitted. And now it probably will not take too much of your imagination that in this situation, you probably get probability of reflection and probability of transmission. So this is very interesting. Particle comes in, it gets reflected most of the time, but there's a small probability that it will get transmitted. That is called tunneling. So this is called tunneling. If I told a person from the street that a particle can pass through a not classical region like that, they wouldn't believe me. But now you might start to believe me because you know that in region 2 here, the wave function doesn't go to 0, it will exponentially decay. And so a tail of the wave function can reach a region 3, allowing the particle to penetrate through this barrier, which is classically impenetrable. So we will look at that tomorrow. And that will be it. So we just discussed basic quantum scattering in 1D today. We discussed reflection coefficient and transmission coefficient. And we will dwell on the topic tomorrow in discussing the quantum tunneling. And that's all I want to do as far as chapter 6 is concerned.